In the last video, we talked about the small increments formula for a one variable function f of x, where we had the change in f was approximated by the derivative of f with respect to x times the change in x. Well, what if we have two or more variables? How can we approximate the change in f then? Well, the small increments formula can still be used when we have two or more variables, but instead of using the full derivative df by dx, we use the partial derivatives df by dx and multiply those by the changes in x, the changes in y, and any other variables we might have. So let's use this relationship in one more example. So here I have the function z is equal to f of x, y is equal to x cubed y to the power of 6 minus x to the power of 5 plus 2y. Using derivatives, I'm going to find the approximate change in z if x increases from 2 to 2.2 and y remains constant at 2. So I'm going to use the small increments formula to do this. So I have a function in terms of x and y. I'm going to need the partial derivative for each. Df by dx is going to be, now when I calculate df by dx, my x's are changing, but my y's are treated as constants. It's the partial derivative. So I get the derivative of x cubed times y to the power of 6. I'm going to do the derivative of x cubed, 3x squared, and y to the power of 6 is simply a multiplier. Doing the derivative of negative x to the power of 5, it's going to be negative 5x to the power of 4. And then doing the derivative of 2y, I'm going to treat this as a constant, as I'm looking at the derivative with respect to x. So that would be 0, and I can ignore that. Now doing my partial derivative with respect to y, I'm going to look at y as my changing variable, and I'm going to treat x as a constant. So for my first term here, I'm going to have x cubed times 6y to the 5th, or 6x cubed y to the 5th. For my second term here, negative x to the power of 5th, I'm going to treat it as a constant as I'm doing the derivative with respect to y. Thus, this derivative is 0. And for the third term, plus 2y, the derivative is going to be plus 2. So now I have to calculate these partial derivatives based on my current coordinate. So based on the information here, it says f is going to be increasing from 2 to 2.2, meaning it's currently 2. So x is equal to 2, and y is going to be remaining constant at 2, meaning y is also currently 2. So calculating my partial derivative, I'm going to have 3 times 2 squared, my x is 2, times 2 to the power of 6, as my y is 2, minus 5 times my x value is 2 to the power of 4. And this is going to give me 688. Now I'm going to repeat this process for my partial derivative with respect to y. I have 6 times my x is 2 cubed, times my y is 2 to the power of 5th, plus 2. And this is going to give me 1,538. Now I can use the small increments formula to estimate df by dx. Now df by dx is 688. And the change in x I'm looking at, I'm going to write my new value of 2.2 minus my old value of 2.0. Plus df by dy, 1,538. And now my y is not changing, so the change is going to be 0. Working this out, I get the change in f is approximately 137.6. That's the estimate for the amount of change in f. Now we have the same function here for part B, but now we're going to estimate the change in z when x increases from 2 to 2.2 and y decreases from 2 to 1.9. I'm going to use my small increments formula again, and I've already calculated my df by dx and my df by dy values. When x is equal to 2 and y is equal to 2, df by dx is equal to 688, and df by dy is equal to 1,538. And these are the values from part A on the previous slide. Now I'm going to approximate my change in f using the small increments formula. Df by dx is 688, and my change in x is going to be the new value of 2.2 minus the old value of 2.0 for a change of positive 0.2. Df by dy is 1,538, and my change in y is going to be my new value 1.9 minus my old value of 2 for a change of negative 0.1. This is going to correspond to an increase positive 137.6 and a decrease negative 153.8. So the change in f is going to be approximately negative 16.2. And what I can see here is that the change in x tried to increase the f value, but the change in y was decreasing the f value, giving me a net change of negative 16.2. Again, approximately negative 16.2. And that's how we applied the small increments formula. Let's have you try it now.